it will all work. Okay, I hope you can all see that. I'll take that as a yes, maybe.
Yes, we can see you without a beard.
Great. Okay, so welcome everyone to this my first seminar here at UCLIC. So today I'm going to be telling you a bit about my research, which, as Anissa was saying, is about creating 3D experiences that you can see and feel and interact with in front of you without wearing anything onto you. So I wanted to start by introducing myself a bit, as I'm still a bit of a newcomer. I'm Diego Martinez Plasencia. I was born in Spain in 1982, and I'm the proud father of 3 beautiful girls, Africa, Nadia, and Zoe, which you can see over there, together with my wife, Alicia. During the years, I've been working at the University of Castilla-La Mancha, where I did my PhD and was working in Belgium for a little bit, then as a postdoc in Bristol, and already as a lecturer at Sussex and now at UCL. So I define myself as a researcher in HCI and 3D displays. But back in time, I started doing research in multi-user VR worlds. So this was as part of my PhD in the Instituto de Investigación Informática de Albacete. And for those of you who don't know, multi-user VR worlds, they are virtual reality environments meant for several users who can be on the same space, but usually they are not. And I was automatically fascinated by the potential of these kind of experiences, because they allow you to create this kind of shared environments in which these people can share and interact in it. And in this case, this is a meeting room in which they could share presentations, talk, and collaborate. But at the same time, not everyone needs to see the same things. Like in this particular example, for instance, that big screen was always shared, but each user also had a personal screen that only they would be seeing. And they could use that maybe to check their notes. They could also share it with members of the group. So if somebody was saying something that was not right, or you need to provide some data, you could do that and only they would see it. You could affect also the audio. And in a way, I was fascinated by this kind of a dream in which you have full control of the environment and the reality that users would be experiencing, and about the whole potential that could be bringing in terms of collaboration. However, back in time, this was what would be also involved in getting the most of these kind of experiences. Devices were heavy, they were very intrusive, like they had really lots and lots of wires. And that's what led me to realize that as much as I love the potential of these kind of interfaces, all this instrumentation was putting the benefits of these kind of environments behind the technological boundary. So users need to prepare before they can get those benefits. And then at the same time, if once that I am in VR, I realize that, oh my, I need to check my phone, my notes, I need this or that, I need to take all that off, check it, then get back inside. So in a way, it's something that is really separated from our environmental reality, is something that we need to pay a price to get the benefits of. And if you ask me, I believe that these kind of interfaces should be a lot more like maybe what we see in movies, something that is right there in front of you for you to see and explore and interact with, just when and as you need it. Something that blends in with your real world, with the tools that you might be using, like that pen that he's using, or even your own body. When it is this seamless, that's when the full potential, these kind of interfaces will be unleashed. And well, I'm also quite inspired by these quotes from Arthur C. Clarke, that any sufficiently advanced technology is undistinguishable from magic. So these kind of experiences, and moreover, as we see them in movies, they are really valuable and compelling, only because they work without us having to worry or do anything about it. Over my years as a researcher, I'm trying to create this kind of magical 3D interfaces right there in front of you. And this has usually involved a mixture of 3D display approaches, but also creating systems taking into account like the properties of the material, both physical and optical properties, and many times exploiting simple physical phenomena or principles that we can use to create a display that adapts to our needs. So I'm going to be taking you through a few of these, and I wanted to start with Pivot, which was a system that we submitted back in 2012 to UCLIC. This is a tabletop system, okay? But when you lean forward, you get to see additional content, and that's a personal content that only you will be seeing. That creates this kind of paradigm of a shared space for the tabletop, like these users collaborating over a map, maybe planning a trip. But then it also allows other users, like that one, well, he's placed something over there, and we don't know what's that. But if we take his viewpoint, he's getting personal overlays, additional information. And this might be just him getting interested on a particular monument, like Pisa Tower over there, or just needing to break apart for a few seconds just to check a schedule, check when a museum is open, and then actually being able to feed that back to the rest of the users. This ability to have a shared space for us to collaborate, keep track of what we are doing, but at the same time support those individual tasks and easy transitions between them. That's something that can be very valuable for collaboration. And the way this works, as I was saying, involves a bit of a combination of display approaches and materials. And particularly the material or the key material that we were using over here is called Lumisti. This is a directional diffuser. So over here we have a sheet of Lumisti. It is pretty much transparent. Over there we have a projector. And when the light is hitting it almost perpendicularly, we can see that it is pretty much transparent, and we can see the projection on that piece of paper. However, if we change that orientation a little bit, you will see how these dots disappear and the brightness of what we were projecting increases on the material. So that way, you can have the light either going through or visible on the material itself. And then if we go back to a perpendicular state, this would be when we lean forward. Again, the projection goes through and we get to see more of what's underneath. So how were we exploiting these properties of this material? So it worked a little bit as we are saying. What we wanted to do is create a space which was shared, a shared view for everyone who was sitting over here to the right, but anywhere around the tabletop, and have the ability of seeing something different when you lean forward. So for that, we were using the Lumisti film and projector, and that way, the view from the projector would be visible when you were standing to the side. But then as you lean forward, what you would be seeing is a liquid crystal sandwich. This is an auto stereoscopic display. That's a display that allows you to see 3D without glasses, and actually only you from that specific position can see it. But you can think of that kind of as an advanced Nintendo 3DS display. So just an example of how by combining display approaches and exploiting the properties of the material, we can create novel display approaches. Another approach in which I've been working a lot is actually with fog screens. So this is an example we also created a few years ago. We are using a fog screen, which is a thin layer of fog on which you can project, and that gives you your personal space where you can interact. But you can also share it onto the tabletop, again, working as a shared space for us to collaborate. You can share it with others can take it to their personal space, or if they are not interested, they can maybe bring it back to your screen. And in this case, this kind of digital information becomes something which is almost tangible, like you can have it for yourself, share it with others, and altogether we are all keeping the attention in this shared space in which we are collaborating, but we can tailor how we display the content to our needs, either for my personal space, to share it with others. So that gives you a lot of flexibility. At the same time, being made of fog offers lots of possibilities for 3D interaction, which is quite similar to that of VR. You can just reach through and manipulate objects with your hands. You can augment real objects. If you don't want anyone to be drinking from your teacup, you can sort of put your name on that. And in a way, it creates this kind of a seamless space where several people can interact both with 2D and 3D information and in personal or shared spaces. As I was saying, I've been working with fog quite a lot. I also wanted to share the following one because I find it quite an interesting system. So we called it Sensa Bubble, and it is a device that creates soap bubbles filled with fog. By filling them with fog, we can track them with a depth camera, and we can also project onto them. That creates a kind of a visual information, but then also the fog inside, we add some smell. So it's not only that you get a visual notification. We were testing colors, icons, text. That is kind of a short-lived notification that is only going to last for a few seconds. And it is not so different from the bubbles that you would get in your monitor, reminding you of the next meeting, or no, you're running low in space in your hard drive. But by filling them with smoke, we give like a longer duration to that notification. So if you just went to the toilet and somebody sent a notification, say, hey, let's go for coffee. Maybe that bubble with a notification could be filled with that coffee smell. So whenever you come back, you smell it and you say, whoa, okay, let's go. Or I don't know, just imagine that you walk into a shopping center and you get a bubble floating towards you with the logo of Coco Chanel onto it. You pop it and you also get the fragrance of that new perfume that they are releasing. That is kind of a marketing campaign right there in a few seconds. And something that I find very interesting about this display is that it is an attempt to try to capitalize on all the empty space that we have around us. Like usually displays are constrained to screens, walls, like you can project on the floor. But if you look around you, most of what we have is air because we need to breathe and we need to move. This is a way of trying to use that space, which is yours, to also give you notifications, and in a way of allowing the computer to just reach into your world and also have those physical, add those physical elements whenever and wherever you need them. So 2 examples of displays created using fog in this case. But the thing is that the more I got to work with this kind of materials, the more I kept finding interesting properties. So one of the properties that I found very interesting was the way that fog scatters the light. So if you have a patch of fog and you project some light onto that, then if you measure the brightness around it, you're going to get something like this. Fog is very bright if you're looking straight onto the light, and the brightness decays as that angle increases. So this allows approaches such as this one. Over here, they are projecting several views of a 3D model, a bunny, from several projectors. Over here, we are seeing the side of the head. But as we move, now we are seeing the front of the head. The way this is working is quite simple. There is simply some fog and several projectors showing different perspectives. But then as the user moves around the display, he is going to get different views of the content. This is an approach which is compatible with Sensa Bubble or Mistform that would allow you to get that 3D effect even without glasses, and relies directly on this kind of directional scattering. However, it also has its inherent limitations. So if a user is to stand in this transition zone or this overlap zone between two projectors, that user is not going to see a clear image. It's going to be an image which is an addition of both of the contents that you are projecting. And the display might know the content that it wants to present to the user, but it cannot control where the user is standing. So, however, if instead of that, we could control the location of the fog, we could tailor what the user is going to see as to maximize or improve what that user is going to perceive. So again, instead of forcing the user to behave on a specific way, let's put that kind of a burden onto the system and allow the system to be able to make sure that that user is getting the best view or the best experience. And we started playing with this idea in several ways. The first one of them would be the following. We called it Mistform, and it is a shape-changing fog screen. So this provides like a lot of flexibility in you tailoring that workspace however you want, maybe to allow you to reach the content from more economic locations, or just simply adapt it to your needs. It comes with its own challenges. As you are projecting on a curved surface, content is going to be distorted. However, if you know the shape of the screen and where the user is located, you can correct for that. So you can make sure that any content that you present keeps the right geometry. And even if the brightness from fog is not even, as we were saying before, it's quite directional, you can also correct for that. But the thing is that once that you, by understanding the properties of the material, once that you take into account those things, it can also open new possibilities. Like we were talking about ergonomics, it has some benefits also to avoid divergence versus accommodation, which is related to eye fatigue. That happens with HoloLens, VR headsets, pretty much any 3D display you can think of. But one that I found quite peculiar was the following, and it is again related to supporting several users. Over here we have 2 users and a convex shape for the screen. This allows them to, each of them, get the right perspective on the content that they are sharing, and at the same time, so we get to see the view that we want to see properly, but the content of the view of the other user, the visibility also gets minimized. So that allows us to simply, by putting that burden onto the system, to get better support for collaboration. So understanding and exploiting the directional properties of the diffusers as a way of creating novel types of displays. Another opportunity that I was also looking into and that I found quite interesting was actually the chemical properties of this kind of fog. So fog particles are actually polar molecules, okay? So they are usually made of water droplets or glycol droplets. This is a water droplet, okay? And this is usually how we see it. These polar molecules, when we see them in a textbook, they always have this asymmetric distribution. And that's not because they like it. That's because this is representing that these molecules have an electric dipole. Like they are not symmetric electrically. Like one part of the molecule it has a bit of a negative electric dipole, and the other one has a bit of a positive charge, we could say. What that means is that these kind of molecules inherently react to electric fields. So if we put them inside of an electric field, they are all going to align towards that electric field, and they are also going to react to that. You can attract them or repel them using electric fields. That basically means that we can use electric fields as to control their position in space. So if you have some electrodes connected to a negative pole, and then you put some particle inside, this could be just an aerosol droplet, or it could be a bubble. That particle is going to follow that path. So if you do that with a fog screen and you also have some electrodes onto the right-hand side, if you start charging those electrodes, you can change the shape of your screen. So we started playing with this idea, and we created a charging process as to further increase the reactivity of the molecules to that. And with that, we could control the trajectory of bubble displays or even the curvature of fog screens. So with this, we are no longer limited to moving the screen in depth. We could also control the curvature, or in general, just move diffusers in space. So again, types of novel displays that you can exploit by leveraging physical properties of that material and combining that with the right display approaches. And this is something that I found interesting because, as I was saying, it was a way of allowing the computer to break out from its case and just reach into the physical world in which we are living. Another approach in which I've been working quite a lot lately is the following, but I would like to maybe open this one for questions and see if you know how this one is working. Okay, what we have over here is volumetric content created in the middle of the air. It is just right there in midair in a completely open space, allowing you to reach inside and without any kind of boundaries or anything like that. This is another example. We have a user, some content, and we can see how the user can reach into the volume or even completely enclose that content with its hands. So, do you know how this one is working? Anyone wants to take a guess? Hope you are.
It looks like magic.
Yeah, so we actually intentionally rolled up our sleeves to do it, you know, to see like there is nothing here, nothing there. Okay, so this kind of a display is using ultrasound. So ultrasound are just like sound waves. They are mechanical waves that they deliver pressure through space. And in case you're not very familiar with how this works, you might be a bit more familiar maybe with UCLIC, which is a technology that uses ultrasound to create pressure points in the middle of the air that you can feel. In case you're not familiar, I'm going to use this video because it's also going to help me explain some bits later on. Whoa, something happened there.
We use a small collection of ultrasonic speakers, just speakers that emit sound waves that are too high frequency for you to hear. And we trigger these speakers with very specific time differences between them, so that the sound waves from each speaker arrive at the same point at the same time. And because sound waves are just pressure waves moving through the air, at that point, all of the pressure differences add together, you get a very localized point of high pressure, and there's actually enough force generated there to just slightly displace the surface of your skin. We can control that, turn it on and off in order to create a vibration, can create any vibration that your hand's capable of feeling, and we can manipulate and sculpt the acoustic field rather than just creating a point, create a line or a 2D shape or even three-dimensional shapes and objects.
Okay, so as I was saying, ultrasound as a way of controlling pressure into space. I really like this image over here. That's it, because I think it explains how it works really well. So each of the sources is creating waves that they are pushing and pulling into the air. The thing is that this technology, what it does is that it takes into account the distance between the transducer and the point where you want to create the effect, so that all of the waves from all of the transducers arrive at the same time. They push and pull onto that point, all in sync. That maximizes the pressure at that point and creates a point of high pressure that you can feel. So this is kind of the simplest thing you can do with this kind of ultrasound technology. But another thing that you can also do is levitation. So for those who might not know, acoustic levitation allows you to trap particles in the middle of the air And it even allows you to manipulate them in space, moving them up, down, however you want. So in a way, this was kind of ideal to have a material that allowed you to provide a physical display element in space that you can control freely while keeping this kind of an open space, totally reachable, and not being harmful to the users. So I started tinkering with this idea with different kind of approaches. The first one that we went for, we called it Leviprox. So in this case, we were using these particles as anchors that we could levitate, and we were attaching them to very lightweight pieces of fabric. We were also tracking them and projecting onto them to create this kind of meter displays of arbitrary shapes. So with this, we could create these displays that we could control into space, which can be used to either for interactive storytelling. The props themselves are meaningful and you can control them and animate them. You can get rid of those pesky old post-its and just replace them by totally meter post-its. This is extremely useful for many of us. You could physicalize games, and this is a bit what I was saying. We can break out from the computer case and just bring this kind of interactive space into our real world, or as we were seeing already, by controlling the position, the orientation, and the projection onto the screen, just create levitating meter displays. And well, but this is all very nice, but this is still not explaining how that content that I was showing you before is actually working, because what we were seeing was something, an object which was purely made of light floating in the middle of the earth. So how does this work? So it is actually quite simple. Like, even if we are seeing a trace, this is only made of a single particle. But that particle is moving so quickly that when you do that, you stop seeing the particle, and what you see is the volume that that particle is following, which we can also color to create this kind of volumetric content. All of this is using transducers, just like UCLIC, which are just tiny sound sources, and we use that to trap the particle. So over here, you can see what one of those levitation traps look like. This is going to show the pressure around them. And you can see that there are 2 points of very high pressure around the particle, like squeezing it as if it was our fingers. We move that very quickly to reveal the shape. And we can still create points of high pressure that you can feel. So if you put your hand over there, you would get a tactile sensation. On top of that, we can modulate the output of the transducers to create sound.
3, 2, 1, 0.
And with this, we were in front of the first display approach that could create volumetric content that you could see without any kind of eyewear and right in the middle of the air, with the additional benefits that it could also create tactile sensations or even sound, all of it coming from the same technology, in this case, ultrasound transducers. This was not so much enabled by any breakthrough in physics. Over here, we were using just conventional levitation traps. The key to making this display possible was in computing those acoustic traps quickly enough. In this case, we were computing 40,000 levitation traps per second, and that is crucial as to allow you to move the particle very quickly. That's what you need if you want to create that kind of volumetric content. It is a bit like old screens. In old televisions, there was only one ray of pixels that was scanning across your television, but it was happening so quickly that your eye would see like a complete image. This is doing the same, only that instead of having a point on a 2D surface, we have a point in 3D. This is something that we've been working on for quite a while, and we've been making quite a bit of progress. So in this project, instead of using a single particle, we are using many. So in this outline of the face that you are seeing over here, this one is actually made of 6 particles. We are using 3 particles for the outline and then 1 particle for each of the additional features. Like in the end, the acoustic power that the device is delivering is the same, but this allows us to control it much better, like just providing more strength where the features are more sharp, or less strength or power where they are softer. It has allowed us to create much larger content, while the butterfly you were seeing before was like 1.3 centimeters in diameter. This is already 9 centimeters. And by having several particles, with a single particle, you will need the particle to be jumping from one feature to the other in order to reveal the whole of the thing quickly enough. Over here, particles only need to stay in the region where they need to reveal the content, and that allows us to make much better use of the acoustic power. All of this still relies on computing this kind of sound fields or acoustic traps very quickly. This is happening in the GPU at 10 to 20,000 times per second, but it is still real time. So that is key as to allow us to have interactive experiences. Like in this case, we have a little animation, but if the user approaches the hand, it can get scared or it can blink its eye. All of this is still compatible with all modalities. So we are creating a tactile sensation here. And if you hear in the back that woo that was sounding, that's actually sound coming from the ultrasound transducers. So still capable of creating larger and more complex content and all 3 modalities. So this is an approach in which I am quite interested. We've got plenty of challenges ahead of us, which we are currently exploring. And again, this in turn demand higher and higher understanding of the physical properties of these phenomena that you're dealing with and these materials. But these are the only way forward if you want to take it to the level of other display technologies. Like over here, I'm showing what happens when you try to render a triangle. So I'm just going to be creating the trap along the edges of a triangle. But as you can see, you don't get a perfect triangle. You get this kind of wavy patterns, and it is distorted. And this is something that the moment you start looking into how the system works, it actually makes a lot of sense. We are not trapping the particle with a kind of a rigid joint. It is more like we are holding it with a spring. So when you create a trap, this is how forces distribute around it. So if this is the center of the trap, the particle that would receive 0 forces. But as it starts moving away from the center, you start having an acceleration that pushes the particle back to the center. Yeah, this is what the forces in the horizontal and in the vertical direction. So if we have the particle trapped like that with this kind of a spring model, it makes sense that when I start pulling down, the particle actually overshoots and tries to follow, being pulled by that spring. This is something which is quite inconvenient when you're creating content, because usually you only care about the shape that you want to get. And this is one that we are approaching by taking into account the dynamics of the system, so that the designer or the content creator only needs to specify the content that they want to see. And based on these dynamics of the system, we compute what the acoustic traps actually need to do. So, well, so defining content is real hard. Only care about the shape, but I would also need to care about accelerations and other properties that I don't want to care about. We are trying to get rid of all those issues. Other issues that also appear come from reflections. If we truly want to allow people to reach inside and interact in close proximity to this content, right now we are assuming that the space is empty. So the moment that you stick your hands inside, ultrasound starts being reflected from your hands, and that can affect the traps. So we have started working into adding geometries, initially geometries that we know, but they can be arbitrary. And by taking into account this kind of reflections, we can still have accurate multi-point levitation. Now the challenge over here is to actually do this in real time, as to just add contents and have it still work. This is something that we are still working on too, but this is a step that we need to follow. There are really many other challenges, but these are just a few. But in any case, more than focusing on all these challenges, because as I say, there are many, I wanted to kind of reflect on this kind of an approach. We were saying how any sufficiently advanced technology is indistinguishable from magic. And in my case, I've taken the path of trying to realize this kind of technologies by exploiting display approaches, but also understanding of the physical phenomena that can help us create those interfaces. And well, this has usually involved like getting a bit quite deep into these aspects. But that has put me kind of in a position in which I'm kind of driven by these dreams or these magical interfaces that I want to create. But this usually involves a combination of also like physical phenomena that can help us create them, and technological approaches that help us use them. So that's a bit the corner where I am sitting, and this is just like a very narrow view of what creating this kind of seamless multimodal interfaces would entail. Like HCI is much broader than that. Like we also would need to take into account like the interests of our users, their context, even their local communities, or where these things are going to be deployed. But what I want to pledge a little bit over here is that us as HCI researchers should lead the creation of these kind of technologies. So usually we are using display technologies and elements that are created by others, by engineers, and they might be missing that insight of what it is that the users need. And as we have been seeing, the kind of physical phenomena and technologies that we are exploiting can heavily influence the affordances that the system can provide. So in a way, we want to lead the kind of interactive experiences that we know our users need and find the best way of creating them. We really need to exploit this kind of a space. Like from my side, I'm kind of happy in my little corner, even if I know it oversees many other aspects that are also relevant. And I continue to try and work into this space to try and make, through the use of appropriate technology and techniques and exploiting those physical principles, to just allow us to get access to those dreams without having to care about the underlying physics. With this, I would like to finish my talk. And if you have any questions or anything like that, I'm happy to take that.
Thank you, Diego. I'm going